Machine learning has achieved a great success in the last few years, in many different areas, but at the same time it still struggles in applications such as medicine or finance. One of the reasons because of that can be that machine learning models are not able at the moment to embed causal reasoning during their decision-making process. As part of this project, I therefore decided to examine different approaches which can be taken in order to fill this gap. As main case study for this project has then been considered epidemic modeling, and in order to aid the understanding of the reader, have been created two different online resources in order to make possible to play with different models and parameters. As part of this project, has then been decided to examine two different types of modeling techniques, compartmental modeling and agent-based modeling. In this web application can be found both of them. In the first tab, we can find information about how COVID-19 has been spreading around the world in the last few months. In this case, we can find specific information about each country or estimates of the number of deaths in how they changed in the last 24 hours, and videos about how the disease has been spreading around the world in different countries for number of cases, deaths, or recovered. In the second tab, we can instead find news about COVID-19 around the world. Using the drop-down menu, we can pick the country we're interested in, and then we can find articles related to the day. News are fetched every 2 hours, while data about COVID-19 every 24 hours. At the end of the page, we will then find also a summary of the sentiment of the day regarding the news that we fetched. So we can see, for example, that this day the overall sentiment about COVID-19 in the UK has been mostly negative, but not that much. The score is a between a value between -1, which is really negative, and +1, which is positive. Moving on to the third tab, we can then find information about how disease spread and how exponential trends can be identified. Every exponential trend in this ambit is then destined to be converted into a logistic trend. In fact, if more than half of the population is affected by a disease, then that means that there will be less individuals which can be potentially infected, and therefore that will mean that we have reached an inflection point. We're already examining the four different types of agent-based models which have been created as part of this project: population modeling, track and trace, central hubs, and a funnel simulation. Agent-based modeling makes particularly easy to visualize different elements of a population moving 2D. For example, selecting for different isolated communities in this model, we can see how in just 100 days an entire population can be affected by the disease in question. Track and tracing and central hubs can then be used in order to extend our model. As shown in this simulation, track and tracing can be particularly useful by isolating all the infected individuals in a quarantine area. In this way, it makes more difficult for the disease to spread around the overall community, and the number of deaths and infected decrease drastically. Central hubs can instead be used in order to exemplify the role of supermarkets during a lockdown. In fact, individuals during a lockdown still have to go to buy food at the supermarket, and although not all communities might have infected, through a central hub, the disease can spread around the different communities, therefore increasing the number of overall deaths. Finally, has been examined an agent-based modeling simulation in order to simulate how the economics of a community might be affected by a lockdown. In this case, we can see how the number of savings and the financial support requests vary over time. One of the most interesting models created to this dashboard was coronavirus modeling through compartmental modeling. In this case, we can examine Italy as a case study. Here we can see the cumulative results over time, the population age on average of Italy for different bins, and then simulation results in order to see how the R value of Italy change over time and the death probability change over time, depending on if, for example, the hospitals were overcrowded or not. Taking into account also the number of beds available in Italy, it's possible to calculate how many deaths could be avoided in case the hospital sector was not overcrowded, and predict, for example, how many number of beds would have been available in excess. Finally, using machine learning and regression techniques, it's possible to predict the values which Italy went through, and when, for example, the restriction had been applied in time, and what was the maximum R value in the past. Finally, a live A/B testing tool has been included in order to get feedback about the two different models used.